Welcome back to Math 104. Armed with our general formula for finding the probability of exactly k hits on n shots at the target, where the k hits are in any possible order, we are now asked to find the probability that on 10 independent shots at the target, with a 60% probability of a hit on each individual shot, you hit the target exactly 6 times. In terms of our formula, n equals 10, the number of shots, k equals 6, the number of hits that we are inquiring about, and p, the probability of a hit, equals 0.6. We compute the probability of 6 hits in 10 shots to be 10 choose 6 times 0.6 to the 6th power times 1 minus 0.6, that's the probability of a miss, raised to the 10 minus 6 power, that's the number of misses. If we want to write this in terms of factorials, we've got 10 factorial divided by 6 factorial times 4 factorial, times 0.6 to the 6th power, times 0.4 to the 4th power. When we go and compute this, it turns out to equal approximately 0.2508. Here's another example. If you guess at random on a multiple choice exam, with 15 questions and 4 possible answers for each question, let's say A, B, C, or D, find the probability that you obtain a perfect score. This is something we already know how to do by our earlier technique involving just counting, but let's see how it works out using our new technique. We want to use the results of our reasoning about taking shots at a target and apply it to something else. Now there are 15 questions on the exam. That plays the role of 15 shots at the target. We are asking about the possibility of 15 hits on 15 shots. You could say 15 successes in 15 attempts. And the probability of success on each individual attempt is 1/4, or 0.25, because there are 4 choices for each question. So on each individual shot at the target, on each individual guess, there is a 1/4 probability of guessing correctly. What does the formula have to say? The number of different outcomes contributing to this event equals 15 choose 15, which turns out to be just 1, because there is only one outcome in which you get everything right. That's the one in which you get everything right. There is only one way to do that. So the number of outcomes, which is just 1, times 1/4 raised to the 15, times 1 minus 1/4, that's going to be 3/4, raised to the 15 minus 15, to the n minus k, raised to the number of incorrect answers. So probability of an incorrect answer raised to the number of incorrect answers, which is going to be 0 here. Let's see how this works. This is 1, 15 choose 15 is 1, times 1/4 to the 15, times 3/4 to the 0. 3/4 to the 0 is just 1, so this is just a fancy way of writing 1/4 to the 15th power. This is going to be an extremely low probability, but notice that we get exactly the same result by this method as we would by our earlier method. We're supposed to count the number of outcomes in the event, so there's one way to guess correctly on the first question, times one way to guess correctly on the second question, times one way to guess correctly on the third. We're multiplying together 15 copies of the number 1 in the numerator. In the denominator, we're supposed to count the total number of different outcomes in the experiment. That's 4 times 4 times 4, etc. Because there are 4 ways to answer question number 1. Then there are 4 ways to answer question number 2, etc. The multiplication principle of counting tells us to multiply together 15 copies of the number 4. So that gives us 1, if you will, 1 raised to the 15th power, divided by 4 raised to the 15th power. That's the same thing as 1/4 raised to the 15th power. Thus, our new way of approaching these probability computations agrees with the old way that was based solely on counting. Now let's go on to find the probability that you get exactly 80% correctly by guessing on this exam. Now this is where we really need the new method. Now we're asking for the probability of exactly 12 correct, and therefore 3 incorrect. Where did 12 come from? Because 80% of 15 questions equals 12 questions. So So 80% of 15 questions correct means 12 questions correct. By our formula, this is 15, choose 12. 15 shots at the target, 12 hits. That counts the number of outcomes. Each individual outcome is contributing 1/4, or 0.25, raised to the 12. So probability of a correct answer raised to how many correct answers there are, times probability of an incorrect answer raised to the number of incorrect answers. When you go to compute this turns out to be only about 0.0000114. Not likely to happen. But when you talk about getting 80% correct on an exam, what you're interested in really is getting at least 80% correct. You can live with 80%, but you will happily accept anything more than 80%. For purposes of taking an exam, it's natural to ask about the probability of getting at least a certain amount correct. Now we need the probability of 12 or 13 or 14 or 15 correct. There is no shortcut here for an exact answer to this question, although we will see some kind of a shortcut later in the course. We're going to have to do 4 separate computations. For exactly 12 correct, that's 15 choose 12 times 0.25 raised to the 12th times 0.75 to the 3rd, that's what we just wrote down, plus the corresponding probability for exactly 13 correct. That's 15 choose 13, 0.25 to the 13 times 0.75 to the 2nd power. Notice how if there are 13 correct answers, there must be 2 incorrect answers. These exponents have to add up to 15. They have to add up to the number of shots at the target, or the number of questions on which you're guessing. Whatever n is, the 2 exponents have to add up to n. Next we look at the probability of exactly 14 correct. That's 15 choose 14, 0.25 to the 14, 0.75 to the 1. It's not obligatory to write that 1, but it is polite and recommended. And finally, 15 choose 15, 0.25 to the 15, so this is the probability of all correct, times 0.75 to the 0. Again, not obligatory to write the 0.75 to the 0, but it's a very good idea to do so that this term, this expression, will have the same form as all the others. In the end, this is only about 0.0000124. The conclusion, if you're going to take a multiple choice exam with 15 questions, then you should study. Your chances of doing well just by guessing are not good. But here's another conclusion to this computation. Suppose you're the one designing the exam. Suppose you want to make sure that the exam is long enough that someone is not going to slip past you just by guessing. If you need 80% correct to get a good score, then 15 questions is apparently a long enough exam to make it very unlikely that someone could do well enough just by guessing. Having done a few different examples now, we introduce a new piece of terminology, a Bernoulli trial, named after Jacob Bernoulli of the Bernoulli family of Swiss mathematicians. So a Bernoulli trial is an experiment with 2 possible outcomes. These 2 outcomes are sometimes thought of as success, that has probability p, and failure, which must have probability 1 minus p. The idea here is that in the kinds of multi-stage experiments in which the outcomes can be represented as words of a certain length in a 2-letter alphabet, each stage is a Bernoulli trial. That's exactly our favorite kind of experiment in this course, where every stage of the experiment has 2 possibilities at that stage. The experiment as a whole is then a sequence of a certain number of these Bernoulli trials. We've seen a few examples of this. So there was the first example with shooting at the target where p, the probability on each shot of a hit, was 0.7, and therefore the probability on each shot of a miss was 0.3. Each shot was a Bernoulli trial, and when we took 6 shots at the target, that experiment was a sequence of 6 independent Bernoulli trials. Just now we looked at guessing the answer to each question on a multiple choice exam, where there are 4 possible answers to each question. Since there are 4 possible answers to each question, the probability of guessing correctly is 1/4, and we think of each individual question as 1 Bernoulli trial. The probability of success is 1/4, and the probability of failure is 3/4 on each trial. The exam as a whole consisted of 15 independent Bernoulli trials. Another example that's very useful to think of as a model is to toss an unfair coin, which, for example, has a probability 0.6 of heads. Now here, this language of success and failure are less obvious. There are actually many examples where there's no clear notion of one possibility being a success and the other possibility being a failure. That's actually not a problem. The only thing that matters for this method is that at each stage, in each Bernoulli trial, there are two possibilities. One of those possibilities has a certain probability, and then 1 minus that must therefore be the probability of the other possibility. You don't really need a notion of one being success and the other being failure in order to compute probabilities by this method. Here's another example, and this might be confusing at first because it involves rolling a fair six-sided die. Now you might think if we roll a six-sided die, there are 6 possibilities for each roll rather than only 2. That's true, but now we're talking about an experiment in which only obtaining a 6 counts as a success on that particular roll. That means that as a Bernoulli trial, either you roll a 6, that's a success, or you roll anything other than a 6, that's a failure. So in that context, little p equals 1/6, and 1 minus p therefore equals 5/6. Before going on to the next video, consider the experiment of rolling this fair die 5 times. What is the probability of obtaining a 6 on this die exactly 3 times? Think of how to apply this notion that each roll of the die is a Bernoulli trial to answer this question.